All right, recording is on. November 18th, 2020, Math4707. And we are about to shift gears into a new chapter of our book. Maybe before we start talking about that, I did post the take-home midterm exam number 2 that's supposed to start today and ends next Wednesday. Same setup as last time. Unlike the homeworks, you're not supposed to collaborate with any humans, not supposed to consult any humans online. It is open book, open web, but just don't ask humans to put more sources on the web for you. And if anybody has already looked at the exam online, that would be great. Please do look at it as soon as possible. See if you see anything that looks fishy. You'll remember that our midterm 1, we had a couple of typos here and there that would have been a little annoying for people. And so once people told me about it, I corrected them, but best to correct those typos earlier if they're there. All right, any other questions I can answer about our homework that's due this evening and the upcoming exam or anything at all? All right, so as I mentioned last time, we finished chapter 10, which was about matching theory, which is this very well-developed part of graph theory and highly successful. It has good algorithms for almost all of the questions in matching. And we may come back to stable matching and stable marriages at the end of the class when we're done with, say, chapters 12 and 13. But meantime, let's move on to chapter 12. We said we would skip chapter 11, which is sort of a grab bag chapter. It doesn't really have too much unifying it. And talk about planar graphs, which is actually another pretty old subject in graph theory. Some people would claim that graph theory began with Euler's paper on Eulerian cycles. But planar graphs somehow, they also have a connection to things that the ancient Greeks were doing, and they became very, very popular as a topic and more developed in the mid-1800s when people started worrying about the four-color theorem. So the fact that every planar map has a proper four-coloring. We'll come back to that in chapter 13, but let's just first talk about some of the basics of planar graphs. And there's a lot of cool stuff going on there. So let's start with just a definition of what does it mean for a graph to be planar. And it sounds simple enough. It's just a little bit subtle. Definition of a graph, G is, again, usual story. G has a vertex set and an edge set, and we say it's planar if it can be drawn in the plane with none of its edges intersecting each other or intersecting themselves. If it can be drawn in the plane, and by the plane I mean the R2, R squared, with no edges crossing or self-intersecting. Self-intersection is not so much the issue, but no edges crossing is really the important thing. And there's a word in this definition that's kind of the most slippery. We'll see as we do examples, is that this word can. This is a rather slippery term. It's like, what does that mean to say can, and how do you check whether you can be drawn in the plane, even if you haven't been drawn in the plane? So let's do some examples just to start off. So what I want to do is examine this concept of planarity within one of our families of graphs that we've talked about a lot. What about Kn, the complete graphs on n vertices? Which ones are planar? Kn is the complete graph on n vertices. And I'll draw the first few of them. Okay, K1. It's got one vertex, and there it is, drawn in the plane. There's no edges, so no issues about drawing it planar. There's no problem about edges intersecting each other, intersecting themselves. K2 has two vertices and one edge between them. And yeah, as long as I just avoid drawing that edge, looping around and intersecting itself, it's fine. that's a planar graph. It's been drawn that way in the plane. K3 is this. It's got 3 edges, right? And as long as I draw it in the usual way, like as a 3 cycle, it's drawn in the plane with no edges intersecting each other. K4, let's say, has these 4 vertices, and then I start drawing the edges. And there it looks like I've drawn it in a way such that one of the edges, whoops, this edge and this edge are crossing each other. But that was a bad drawing, right? It can be drawn, right, in the following way. It's isomorphic to this drawing of a graph in the plane. As long as I put one of them in the middle, I can draw that triangle on the outside that looks like a K3 and then do this. And so that's actually planar. And so everybody see what I mean about this word slippery? This is a little bit slippery, the word can be drawn. So just because you drew it badly with edges crossing doesn't mean it's not planar. So far, what do we got? Planar, 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 planar. And what about K5? All right, so K5, if I just do it the way that I often draw it, I put the 5 points like this. I start drawing the cycle around the outside, and the remaining ones form like this pentagram on the inside. And that's all the edges, and there are plenty of crossings. But who knows? We might think of trying to redraw it in a way that seems planar, so that it has no edges crossing each other. And you might think, oh, what if I start out with a planar drawing of, say, the first 4 vertices? Let me actually now start labeling the vertices. 1, 2, 3, 4, 5. Maybe I should do it with vertex 1 in the middle and 2, 3, 4 out here. And start with that planar drawing that we have of all of the edges between 1, 2, 3, and 4. And now maybe I could put the 5 somewhere. I don't know. Maybe I put the 5 out here and see if I can draw it planar. Well, no problem connecting the 5 to the 2. No problem connecting the 5 with the 3 without any more crossings. No problem connecting the 5 to the 4. But now I'm running into a problem. I still have to connect the 5 with the 1, and I don't know how to do it. I could try to go in there. I could try to go, through here. I could try to go through, I don't know. Here I'd have to cross 2. You see the problem that I'm running into. I can't draw it, without some crossing. That last edge that I have to put in between the 1 and the 5. Let me see. And you might think, oh, that was a poor choice still. Maybe you should have started with, okay, so let me actually take away some of those things that I drew that definitely are not. But I'll leave that one in just to illustrate what was our point, is that it seemed like we needed a crossing. Let me try again, starting with a nice planar drawing of K4. Oops. Okay, that wasn't so nice, but it is a drawing. Oh yeah, Theo, you're saying it's easier to determine a graph is linear than planar. Yeah, in fact, there are actually decent algorithms for determining whether they're planar, believe it or not. So it's slippery, but they're actually decent algorithms that run reasonably fast. There's something called, I think, the Hopcroft-Tarjan algorithm, if you want to look it up. But you might think, oh, perhaps I should have put the 5 in here, right? That K4 picture, created these various regions of the plane, and I stuck the 5 in the unbounded region out here before, but maybe I should have stuck it in this region. Maybe that would have helped. So let's try it. Maybe what I should do before I do that is blow this picture up, because we'd like to see kind of more clearly. Whoa, all right, I blew it up a different way, but let me make it actually even bigger on the page. Okay, it's getting scary big there. Anyway, this thing's isomorphic to this. And now let's try to do it. So now the 5 has a nice clear path to 2. It has a nice clear path to 3. It has a nice clear path to 1. But here the issue is, how am I going to get from the 5 to the 4? You know, I could try to go through here, but when I draw that edge, it has to cross, it seems, this thing. Or if I tried to go this way, it looks like it has to cross this one. And so we think you do enough playing around with this and other experimentation, you know, with different ways to place the vertices in the plane, and you start to suspect K5 is not planar. Whoop, K5 is not planar. And maybe I'll put that in blue or something to emphasize. But that word suspect is because we don't quite know yet. And William, you were saying, do you need all the vertices to be on the boundary of the region that 5 is in? Is that requirement sufficient in general? No. I mean, if you mean for K5, we're never going to be able to, we will not be able to draw it in the plane. It really is not planar, but I have not convinced you yet. Did I understand your question correctly, or what are you really asking?
Well, I mean, is that condition I mean, that's not possible. Well, like that condition will not be fulfilled, but I'm trying to figure out if that condition, if it were to be fulfilled, if that is sufficient to.
Yeah, that's not the whole issue behind planarity. No, there's more to it than that. But like I said, there is actually a reasonable polynomial time algorithm that will decide planarity for you. And what about, by the way, K6 and K7 and K8? Planar or not planar?
Will they include a not planar part?
Right. So K6, which has all this stuff and this stuff and this stuff and this stuff and this, we suspect is not planar because it contains a picture of K5 in it. So that's one thing that we'll talk about later. Is it's pretty clear if you contain a non-planar graph, one that you could prove had no planar embedding, that's what you call this when you have the edges drawn so that they don't intersect each other. You call it a planar embedding of the graph. If you contain a graph that is non-planar, then you must be non-planar, as what's sometimes called an edge subgraph, meaning you have the same set of vertices, actually even a subset of the vertices and a subset of the edges. And same for K7. I mean, it doesn't get any better, of course, you know, as you get to, whoa, that's not a K7. That's looking like a K8. Let's see, let me do all the ones that are 2 apart. These things get kind of fun to draw. And then all the ones that are 3 apart. Oh my gosh, am I going to get this right? This may be a fool's errand to try and draw this in front of you. I don't know, that's getting close to K7. Okay. And Theo, you said if we can't draw K5 planar, then adding a point will make it planar. That's right. That's a similar way of saying it. Okay, good. So with the complete graphs, we think they stop being planar after n equals 4, but we're not quite sure. And we will become sure later. But let's talk about the complete bipartite graphs. What about these things, KMN, right? Remember, we've talked a lot about bipartite graphs, and we talked about this particular kind of bipartite graph that's complete bipartite. And so let me just remind you how this works. Well, let's draw. So you have m vertices on one side, n vertices on the other, and just all, you know, edges between any one from one side to the other. So let's draw some of these, like K11, K12, K13. These are all going to be planar because They're very silly little graphs. They're actually trees. K11 has an X1, a Y1, and they have an edge between them. K12 has X1 over here, Y1, Y2, and it's a tree. Trees are always planar. K13, silly enough, Y1, Y2, Y3, and it's looks like that. Okay, so K1n is planar for all n. And what about K2 thing? K2 something like well, let's start with K22. K12 and K21 are actually isomorphic. So if one of them is planar, then the other one is planar. K22 is, let's see, X1, X2, Y1, Y2. And we draw it, and looks like there's a crossing, but we can get rid of it, right? This is isomorphic to, if I put the X1 over here and the X2 over there, and I put the Y1 here and the Y12 there, it turns into a 4 cycle, which can be drawn planar. And William, you're saying the can graphs would be very bad if the nodes were on the edge. Yes, exactly. True. All right, K23. What about this one? X1, X2, sorry, and Y1, Y2, Y3. Theo says cycle plus 2 points equals invalid. Not sure what you mean, Theo, but we'll come back to that in a sec. You can explain. What about K23? Is this thing planar or non-planar? What do you think?
Seems not planar.
Seems not planar. It's got a lot of edges. I mean, it looks like
planar.
Sorry, what? I missed it.
It's planar. You could put X1 on like one side of that column and X2 on the other side.
Yeah, I think you can do something very similar to what we did with K22. Put the X1 over here, the X2 over there, and stick the Y's in the middle. And that layout actually, lets you draw it planar. And actually, you can see in general that's going to work. Like for K24, you can draw it as you draw it the bad way, but then you can redraw it as the good way. It's planar. Okay, so K2n is planar for all n. Okay, so what about if, now we said, remember that Kmn is isomorphic to Knm. So we're saying if one of them is less than or equal to 1 or 2, then we're good, it's planar. What about K33? So we got X1, X2, X3, Y1, Y2, Y3. And all these edges between them. And, oh yeah, Theo, what was your question again? You said cycle plus 2 points equals invalid. What did you mean by that? Never mind, okay. So for K33, what do people think? Planar, not planar? Any thoughts? Not? Yeah, it's not. You start trying to draw it. I mean, again, since it contains a K23 in there, just on the X1, X2, and the Y1, Y2, Y3, you can start trying to draw it, starting with a decent picture that's planar for that subgraph, K1, 2, 3. Okay, so let's draw that. And now the question is where to put this one more vertex, the X3, so that we can put in the edges that it's supposed to have to the y1, the y2, and the y3? Well, we could kind of put it out here in this unbounded region. We could put it in here. We could put it in here. And you try them all and you run into problems. I don't know, let me put it in here, x3, and no problem getting to there. No problem getting to there. Problem getting to the third one. If I try to do that, or you might do it. Maybe you think, oh, you should have put it in the unbounded region. It would have easier access to things, but it's still problematic. y1, y2, y3, x1, x2. Put in the k2, 3. Put in the x3 somewhere out here. And it has easy access to 2 of the y's, namely, whoops, has access to this one and to this one, but it can't get to that one in the middle. Yeah, y2 isn't touching the unbounded region, right? And people may have seen this before as like, this is one of these things you occasionally see in, I don't know, brain teaser books. You got 3 houses, you got 3 utilities, and you want to connect up the pipes of the 3 utilities to all the houses so that the pipes don't cross each other. Can you do it? And can you convince yourself? Well, the answer is you can't, but it's a slippery thing to convince ourselves that this is not planar. So we suspect K33 is not planar. And neither is K34 or KMN, where both the M and N are at least 3. But it all rests on us first showing that this thing is not planar. And so what we're going to do is we're going to develop some tools to deal with this slipperiness and actually convince ourselves that K33 and K5 are not planar. And one of the tools we're going to develop actually in this is we're going to get some inequalities. One thing you might start thinking is, the problem with, let's go back to the complete graphs. The number of vertices as you go up is, increasing linearly, like 1 vertex, 2 vertex, 3 vertices, 4 vertices, 5 vertices as you increase the n. The number of edges, right, is n choose 2. That's increasing quadratically. The number of edges is increasing much faster than the number of vertices is. And you might think that's the problem, is like somehow there's too many edges for the number of vertices when you get into the complete graphs with many vertices. Similarly, you might get the sense, right, really there's a lot more edges than vertices here, many more here. Similarly with these complete bipartite graphs, it's when you've got K1n, actually the number of vertices and the edges is growing both linearly. Here it's actually still growing linearly. But the point is, if you let both the m and the n grow, then the number of vertices is m plus n, but the number of edges is m times n. And somehow once they're both decently sized, you get too many edges for the number of vertices, and you can't position the vertices in such a way as to have the edges not cross each other. I'm just trying to give you some intuition, from playing with these things, what you might think the problem is. That turns out to be correct. Oh, William, you're asking about cycles. Yeah, actually, we'll see something interesting. Later on, we'll talk about something that the book doesn't discuss called duality in planar graphs. And there's a sense in which the regions behave a lot like the vertices. We'll find out. And so just like I'm saying, you can't have too many edges based on the number of vertices. You also can't have too many edges based on the number of regions by duality. But let's come back to that later. So we think, having played with it a little bit, we think planar graphs can't have too many edges relative to the number of vertices. When I say think, I mean suspect. We haven't proven it yet. And so this is what we're going to do is we are going to justify this. The way we're going to do it is we're going to, first of all, set up Euler's formula, which is going to relate the number of vertices and edges and the number of regions. And then we're going to get some inequalities and work with Euler's formula and make this precise. So that's where we're headed. Right, it is correct, our intuition. And these inequalities, they're going to come about in kind of an interesting way. So let me actually just make a remark. Remember how we talked early on in the graph theory part about how we should be careful. Are we talking about simple graphs or multigraphs where you allow multiple edges, or multigraphs where you allow multiple edges and self loops? It's always good to talk about what restrictions you're putting on your graphs. This is going to come into play when we discuss planarity. So note that having multiple edges, multiple copies of edges, and having self loops, it will not affect whether a graph is planar. In other words, when you're trying to decide whether a graph is planar or not, you can get rid of multiple copies of an edge. You can get rid of the self loops. And what do I mean by that? I mean, let me just draw something, you know, that's, if I've got a graph, I don't know, I'm just going to draw some crazy thing with lots of, you know, self loops and multiple edges, and it seems like some kind of weird mutant banana. Yeah, who knows? This thing is planar if and only if the associated simple graph, by which I mean the one where you just take out the loops, the self loops, and whenever you see multiple copies of an edge, you just put a single copy of the edge. So maybe I'll number these vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that was vertex 2, and it's got an edge to vertex 1. It's got an edge to vertex 5. Ignore all those loops on vertex 5. Get 2 to 3, 3 to 4, 4 to 5. There were many edges from 4 to 5, but I only put in one copy of each. 10, 9. Okay, so let's think about this. Why do we believe both directions here? This implication and this implication. Yeah.
Well, you can think about it sort of like you're taking all the edges and bundling together. It's kind of like having a bunch of little wires and bundling them together to a cable, and you can push them together into one edge, sort of. And then for the multi-loops, you can just, since they just need to come out of the same node and go back to the same one, you can make them shorter and shorter until they become nothing.
Yeah, actually, one thing you can do, this direction is in fact really, really easy, because you can just erase copies. If I've got a planar depiction of this thing, I just erase the extra copies, you know, remove that one, remove that one, remove that one, where self loops are all extra. When you have self loops, just remove all of them. And when you've got multiple copies of edges, just remove the multiples and just leave one copy, right? That'll still be a planar depiction because you won't have created any crossings by erasing some edges. So I think this direction maybe is the easiest to see. It's the other one where you have to do what you were saying, William, right? In this direction, if you had a planar depiction like this, well, and the 4 to 5, you know, has the one edge. Now you want to make 3 of them. Yeah, make this little bundle of wires really, really, really close. Just sort of follow in parallel that wire and have that one follow that one, and you can get a drawing like that. Anybody see how this goes? And if you want to have some loops added on the 5. Well, you don't know where the nearest spot is near the 5, but there's got to be a little bit of area in there where you can draw tiny little loops if you have a planar depiction. So I think you can convince yourself pretty easily. If you have a planar depiction of this graph, you can create this planar depiction of a multigraph that just created multiple copies of edges and loops. That's basically what you were saying.
Is it possible to have a vertex with so many edges coming out of it that there is no area around? Is that a thing? Because I mean,
Yeah, that's actually a good question. This gets a little bit into the rules of the planar depictions. So what some people do to avoid exactly what you're talking about, because you can have very, very bad examples in topology of like curves that kind of, go in like this and sort of get infinitely close. You do not want to allow, this kind of a drawing where you get infinitely close but never approach or space filling curves. You don't want, I don't know if people have ever heard of space filling curves, where you have a curve and I can't draw a space filling curve, but it basically doesn't leave you any room next to the thing to draw it. So to get rid of those pathologies, and there are some books that do this very carefully, they talk about taking smooth embeddings so that all the edges, when you draw them as curves, they have to be smooth, they have to be compact. There's topological restrictions. Sometimes the way they do it is they say, make it polygonal, like a bunch of straight line segments, piecewise, linear, in other words. So here's a vertex, and this edge has to be drawn with a bunch of straight line segments between it, finitely many straight line segments. Then when you're careful about it, all of the topological problems that you're saying, where you draw some region and you have some vertex with so many, regions going around it, will you be able to find, as you were saying, maybe there's more of them, who knows, but will you be able to find the space to put in a loop? And the answer is yes, if you introduce some of these topological restrictions on how your arcs are drawn. But it is actually an important technical point that we're just glossing over. Everybody okay? All right. So that remark is going to come back when we get some of our inequalities, because at some point I'm going to start saying things like, oh, I'm worried about some graph is planar, whether it's planar. I'm going to remove all the self loops and I'm going to assume that there are no multiple edges, that it's a simple graph. We'll see how this actually helps us to get the inequalities better. So we'll come back to that. All right, so let's talk about Euler's formula. Any questions before we head there? All right, so Euler's formula. All right, this is a relation between the number of vertices and edges and faces, vertices, edges, and regions vertices V, edges E, and regions. Now I'm going to do something funny. Regions F, I'm going to call it, of a planar graph, or faces of a polyhedron. So the way this thing came up originally was not so much in graph theory, it actually came up when people started talking about polyhedra. I'm not going to give you a formal definition of polyhedra, but I'm going to draw some examples that hopefully you've seen before because they're relatively famous. So here's, what do I mean by polyhedra? Some of the most famous polyhedra are Platonic solids. And I'm going to keep track, so I'm going to draw on the side here. V is number of vertices. E is number of edges. And F is going to be number of faces. That's why we're using F, is because traditionally people have used these things. Okay, so there's this platonic solid, this tetrahedron. People seen that before? If we were in class, if this wasn't an online, I would pull out one. Actually, I should have built one for you, but you know, a tetrahedron, it's like a triangular based pyramid. Got a name. And octahedron. Oh, what am I doing? I put this too high. I wanted to put the V, the E, and the F down here. We'll get these in a second, but let me draw all these first. The octahedron looks like this. It looks like two square-based pyramids on top of each other, or touching each other. There's a square-based pyramid, and now I take its base and I make it the base for another pyramid. That's an octahedron. People who've played Dungeons and Dragons, the dice. It's the dice in Dungeons and Dragons. The hexahedron is a cube. So you've hopefully seen these before. And so what's the definition of platonic solids? I didn't give you a definition. We're not done with them. Oh no, I didn't mean to copy it. I meant to highlight it. Platonic solids, they are these polyhedra. Okay, I didn't tell you what a polyhedron is. Let's go back. What's a polyhedron? Polyhedron is when you take a bunch of half spaces, a bunch of planes in three-dimensional space, look at one side of it, and then intersect those. So you kind of like cut off this half space and cut off this half space and cut off this half space and cut it off this one until you've enclosed a bounded region. And that is a polyhedron. I'm not going to define it formally, but it's what they call a bounded or compact intersection of finitely many half spaces cut by planes. Well, platonic solids are polyhedra that have the following property. When you look at their faces, each face is a regular polygon. Now, you know what a regular polygon means. It's equilateral, all the sides are the same, and all the angles are the same. So equilateral triangles are okay as faces, or here we've got squares, right, our regular four-sided polygons. So you insist in a platonic solid, every face is a regular polygon, and at every vertex, you have exactly the same number of faces meeting. So in this one, we've got 3 faces meeting at that vertex. Same at that one, same at that one, same at this one. Here we've got 4 vertices, excuse me, at each vertex we have 4 faces meeting. Same at that one, same at that one, at that one, at that one, and at that one. Here we've got at every vertex 3 of the squares meet, and it's the same for all of them. So the idea is the platonic solids, they're the most regular looking in the sense that all the faces look the same. You insist that it's the same, excuse me, I should have said it's the same regular polygon throughout. All the faces are the same regular polygon, and all the vertices look the same. They have the same number of faces meeting at them. Okay. And so the Greeks were interested in classifying them, and we've almost got the classification here. All right, let me put them in 2 rows. Let's see, who's left? The dodecahedron, which has got pentagonal faces. And this is actually one whose vertices and edges we've drawn already when we did Hamilton's game that he marketed for trying to find a Hamilton surface in a graph. Excuse me, Hamiltonian circuit in a graph. So that's the front of it. And if we try to draw the back, this is always dangerous, but let me try it. There's a pentagonal face in the back. And that's kind of connected to these. Yeah, that's sort of accurate, and not perfect. V, whoops, V, I wanted this in black. V, E, and F. We'll write these down in a moment. And then there's one more, the icosahedron, which looks in the front kind of like this. Oh, that was a bad drawing. Let's try that again. In the front looks kind of like this. And then again, let me try to draw in green these faces in the back that you can't see. There's a triangle there. And I think if I connect it to those, connect that to those and that to those, I think I will have gotten it right. And so let me slide this up a bit. With these things, the number of faces is really easy because it's part of the Greek prefix at the beginning. So the cube is also called the hexahedron. And they're all named for their number of faces. Tetrahedron has 4 faces. Tetra is 4. Octahedron has 8 faces. So F is 8. The hexahedron, whoops, didn't mean to do that. The cube or the hexahedron has 6 faces. Hexa for 6. The dodeca is 12. And icosa is 20. Of course, if we don't remember that icosa is 20 in Greek, then that's not helping us. But I've seen it so many times that I remember it's 20. And so let's count the vertices. Here we got 4 vertices. Here we've got 6 vertices. Here we've got 4 vertices on top and 4 on the bottom is 8. And let's see, for the dodecahedron, let's see, there's 5 vertices on that pentagon. There's 5 on this back pentagon that was in green. And then there's 10 going around the outside here. That's 5 plus 5 plus 10 is 20. 20 vertices in a dodecahedron. And what about vertices in icosahedron? There's 3 here on this triangle, 3 here on that triangle, and then 6 around the outside. So 3 plus 3 plus 6 is 12. That's a 12, sorry, 12. And now the edges is a pain in the butt to count for most of them. It's not so bad for this. You get 1, 2, 3, 4, 5, 6. It's maybe not so bad for this. You get 1, 2, 3, 4 touching that vertex, 1, 2, 3, 4 touching that vertex. 4 around the middle there is 12. In the cube, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Anyway, don't trust me. Check me later. Here, it really starts to become a pain in the butt. Let's see, there's 5 in that hex, in that pentagon. There's 5 in this pentagon. There's 10 going around the outside here, and there's like another 10 that are like these and these. All total, it's 30 edges. That gets to be a bear to count. And here, let's see, there's 6 going around there. There's, oh my gosh, 3 there, 3 there. And then there's like, I don't know, I'm not gonna do it in front of you, 30. It's also 30. Check me later. Enlarge it, put numbers on them. All right, so I'm running over time for us to do our break, but the point is, what we're gonna check after break is Euler says, can't get it out of the way. Euler says that whenever we draw a polyhedron, whether it's one of these highly symmetric platonic solids or not, V minus E plus F is always equal to 2. So if you know 2 out of the 3 numbers, the V, the E, and the F, you can deduce what the third one was. So I really didn't have to do this pain in the butt calculation of the edge numbers. This says that E is always equal to V plus F minus 2. Let's check that. The E here should be this plus this minus 2. Yep. 6 is equal to 4 plus 4 minus 2. 12 is equal to 8 plus 6. That's 14 minus 2. This one's also 6 plus 8 minus 2. 30 is, 12 plus 20 is 32 minus 2. And again, 30 is 20 plus 12 minus 2. Okay. So let's come back and talk more about this after the break, but this formula is going to be crucial for us understanding more about planar graphs, a lot of things about planar graphs. Questions before we turn off the recording? Sorry, I missed some things in the chat. 20 faces. Yeah, that's true, Roy. That's actually a good way to do the count for the 30 edges for some of these, is using the fact that if we take the sum of the vertex degrees, we're supposed to get 2 times the number of edges. That's right. Good. Yeah, and we'll come back to that too, actually, when we do some, we're not only going to do some inequalities, we're going to do some equalities exactly like that. No questions before break? Okay, I'm turning off the record.